I'm Jeremy Lochner.
Matthew Rogers. So we are both freshmen at Auburn University, and we work for an engineering firm in Huntsville called Dynetics. And we got our start into the whole cybersecurity thing through a competition called Cyber Patriot, which is like a cyber defense blue teaming competition for high schoolers, which we were national champions of last year. So we got our inspiration for this whole project we're doing because I guess now would be 2 summers ago. We were messing with a piece of APT malware that we had to reverse engineer. And once we recompiled it, of course, the standard antivirus was unable to detect that it was the same piece of malware, and thus, it didn't catch it. So we thought this was kind of strange that you could just accidentally, run it a few times and bang, it doesn't work. So we were trying to come up with a solution to this problem. So we did some research into how standard antivirus works. And it works pretty well when, of course, the suspicious file matches exactly to what you have in your database. Or maybe, it checks the imports table to see if there's any suspicious activity there. Or sometimes it uses behavior rules with heuristics. However, standard antivirus is sadly not very nice at all times. Instead, it tries to stop you. So, of course, they can use a packer and obfuscate their code, in which case it looks different, so it won't catch it. Sometimes imports are done during runtime, so looking at the imports table doesn't work. Sometimes the antivirus engine is just disabled if they have shellcode access, which of course means it doesn't work. And then of course it could be written custom-made for attack as well. So to come up with these, we came up with some requirements for a solution to all of these problems. So our tool has to recognize malware, even if small changes are made, such as recompilation. Has to be able to check new malware despite being custom written, has to be flexible, and it has to have author identification, a comment system, as well as in-depth scoring and reporting.
So our first step towards this solution was to use function-based hashing instead of file-based hashing. So instead of hashing the entire file with MD5 or SHA-1 or something like that, we would go into the file and disassemble it and get each individual function and hash those with the same, either MD5 or whatever we wanted to use. Then we ran into our next problem, which was standard hashing. The problem with standard hashing is that if there's a small change in the input, then sometimes there's a very large change in the output. So these two pictures are almost identical, except on the right picture, there's one pixel that's changed to gray instead of black in the top right corner. And the MD5 hashes only have two characters that are the same, which might even be coincidental. So to solve this problem, we found something called fuzzy hashing. And instead of using a standard hash like MD5, it uses a mix between standard hash and rolling hash. A rolling hash uses certain sequences of characters and hashes only those parts. So they'll have like a poem or something, and it'll have EM somewhere in the poem. And you'll only hash the parts that end with EM and go all the way through. Usually it's random. And then, so we use the fuzzy hashing on the functions instead of standard hashing, so that we have a small change in input, it'll only have a small change in output.
So we use a program called SSDeep in order to utilize context-triggered piecewise hashing, which produces the so-called fuzzy hash, which makes it so that we can do small change in input equals small change in output. It was written by a guy named Jesse Kornblum. He's written a number of forensics tools, most notably tools like Foremost. So here we have used SSDeep to do our fuzzy hashes. So again, we have these same two pictures of a Saturn V rocket. The one on the right simply has a single pixel changed, so it's pretty much impossible to tell. And as you can see, anything highlighted in red is where the hashes are the same and in the same position, and there's only two characters that are different. This is because we barely changed it, so of course the hash also barely changes since we're using fuzzy hashes. And as Jeremy was saying earlier, how this works is that it will take a rolling hash and to get rid of the fixed block size problem, which is why we have unhighlighted at the end of each of these lines and then an ME. And then from there, it'll take a traditional hash of those rolling hashes, which you can see on the right. And then from there, it takes the least significant bit of those traditional hashes and creates the fuzzy hash from that, which is the block on the right. So as you can see, we do this, and then we change Happy Days to Matt Rogers. And from there, the entire traditional hash changes, but only a single character, the fuzzy hash, changes in response.
So our solution, or our implementation of these concepts is a program that we call Malfunction. The name sounds kind of like something's going wrong, but hopefully we're trying to fix our problem instead. These are some of the alternative names that we came up. My favorite was Flim Flam, of course. Most of these are backronyms that we came up with whenever we were bored. So the philosophy behind Malfunction is that it's not us versus a computer, it's us versus the person behind the computer, and most of the time they're really lazy. Pretty much only comparable to college students almost. They'll usually go on like Stack Overflow. We've even found exact questions for pieces of malware that we have where they're like, how do I do this thing? And then they just copy and paste the solution in the first answer into their malware. And so if we look for that, we can almost identify where exactly it came from based off of our fuzzy hashes.
So we first realized this around 2 summers ago because literally we were reverse engineering it and we found this giant write-up on like an outdated encryption system like on codeproject.com that they'd copied like text for text, no variables are changed, nothing. It was incredible. So keeping to our brilliant naming scheme, we have Malfunctions functions. We wanted to make a Schoolhouse Rock joke somewhere in here, but it just sounded dumb. We have mallearn, malfunction, and malget. Mallearn just adds the signatures of a known file to a database. Malfunction analyzes our unknown file, and that's where we get our analysis. And then mallearn and malfunction are wrappers for malget, which will acquire the signatures from a binary that can then be used to feed into those tools. So in order to keep all of our hashes and binaries and things like that, we use SQLite 3. We use a relational database structure, many to one, so functions to binaries, because obviously you have many more functions than you have singular binaries. So what we do here is we have 2 tables, functions and binaries. The functions table includes the function hash, which is just the SSDeep score, or the SSDeep hash, fuzzy hash, and then the binary ID is an MD5 hash of the binary that it came from. And we use that to link it to some more in-depth information about that binary. So for instance, we have what author it might have come from, so that way you can detect it in the future, maybe a file name that it was originally under, any comments you have, as well as a trust level, which we use blacklist and whitelist. Basically what this means is you say whether you think it is benign or malicious. In addition to this, we also store file types so that it will run faster in the future.
For a disassembly process, we use the up-and-coming news, super popular Radar E2. I don't really know how to pronounce it. I don't think anyone does. But what we use it for is the disassembly, and we only use the disassembly to get the function start addresses and their lengths. So we look at all the calls and we get the function addresses and lengths, and then we snip them out manually so that we can hash them all.
It's also much better than the very expensive IDA subscription, and I think it can make tables as well, so might as well.
So here's our process. We use Radar2 to get all the function lengths and their start addresses, and then we snip out each of the functions manually, and then we fuzzy hash all of them, each individual function, and then we send them to Mallearn to either learn them to the database or to Malfunction to analyze them. And Radar2 works with tons of different types of executables, from anything from native Windows and Linux binaries to things like NES and Game Boy games.
So learn mode is pretty much the foundation for it, because obviously if you're scanning in, say, an empty database, there's not much really information you can pull from that. So here's an example of learn being run. So here you just do python mallearn.py. So here we assume that the file trojan.exe is malicious, so we give the blacklist tag. It's written by some group called Scary Panda. The file name was, say, it's disguising itself as like svchost.exe, and you can leave a comment there as well. And then it would gather the file type just by analyzing the binary. Malfunction is very simple to run. All you really have to do in order to do it is give it the just Python malfunction, then give it a file name, and from there we can do some analysis and run some tests on it. So once you give malfunction an unknown file, it will load in each database into memory, and then will iterate over all signatures of a matching file type. So that means if you have, say, an unknown file that is like an ELF, then it will only scan against other files that are ELFs. This saves a lot of time when you have a massive database, because otherwise, I mean, if you imagine just scanning over every single function that you have stored to every other function that you have in your file, it can take a long time. So this really cuts down on our time. though there is a flag that you can add if you want to scan over the entire thing. Then from there, we use SSDeep's built-in comparison function to generate a score to each function. And how the scoring works is it's like a 0 to 100% kind of scale. So 100 means it's an exact match. A more mid-range score might mean it has some like similar functionality, or it's similar at least. And a 0 just means it doesn't match at all. And from there, we keep track of what list it's on, so blacklist or whitelist, as well as what binary the function was from. So for our analysis of it, because of how SSDeep works and how fuzzy hashes are, we have to throw out any functions less than 20 bytes long, because those just really skew our data. It's very easy to have a match between a very small function that has been fuzzy hash and just a larger file, because the chances are it's somewhere in there. And because of this, we also have to do some weighting after that. So how the weighting works is it's dependent on how long the function is compared to the total length of all of the functions in the file. So from that, say you have a strong blacklist match with a very long function, that strong blacklist match can outweigh a bunch of very small functions that have a strong match in the whitelist, enabling you to say it's malicious as opposed to good in this case, because you have a longer function. And then after that, we compute a total malware score, which has like our % chance of it being malware. And then we just output more results. So this is a somewhat weird slide on how to calculate our malware score. So like I said earlier, we take all of the functions that are less than 20 bytes and throw them out. Then we get all of our function scores, and we do our weighting, which is just function lengths over the total lengths times each function's respective score. From there, we go and associate the scores on a binary level. In order to get more meaningful data, we throw out any binary scores that are less than 25. And then from there, we just take the average scores that are in the blacklist and the average scores that are whitelist, and then do whitelist minus blacklist binary scores. And that is our total malware score. So that's from negative 100 to 100, a negative number being most likely malicious, and a positive number being benign.
So here we have one quick example. We have 3 files executables called alpha, beta, and gamma.exe, and each of those have one function also called alpha, beta, and gamma respective. And they're all written by the same person named Scary Panda. And here are their file names, authors, binary hashes, and some random comments that we came up with. And then we also have one more file called unknownfile.exe, and it also has one function. So we want to analyze the unknown file. So we check the SSDeep score between the one function in the unknown file and each of the other functions, and we get their score. So we can tell from the score of 90 with alpha that is very, very like our unknown function, and so we think that those files may have a similar purpose. And then function beta and function gamma also have really high scores. Usually somewhere around 40 doesn't mean a whole lot. But once you get up to 60s, they're kind of similar. Once you get up to 90, they're almost exactly the same. There might be some print statements or something that are different. And due to these scores, we can tell that this might be a malicious file, or it's very likely to be. So here's our output for that. We have the whitelist average score and the blacklist average score. And since the blacklist average score is so much higher, it has the gradient goes to the left, and it has a negative score because it's probably awful. And so we have the beautiful gradient for output, and that took like 68 lines of code. It took like a whole day. It was amazing. And then it has the possible authors. We don't know this one. And then it also has possible file names that it might have either hidden as or that it was really, really close to. So it is all command line driven. Right now it only works in Linux. We started out this project wanting it to be Windows compatible, but a lot of the dependencies we have were super impossible to build. Or we wanted to use some of the native Linux functions for getting some of the file names or checking if there are things that are packed. It also has no interactive input after you do the initial argument, so it just runs itself. If you put it on a folder, then you can come back later and then everything will be done. You don't have to do anything after that. It works for all x86, x64, Linux, Windows, OS 10 binaries just fine, and even there's a gigantic list on the Radar website. It detects lots of similarity between malware, and it makes it easy to tie binaries to authors if there's super similar scores on a bunch of functions. So our summary, lots of APT malware bypasses normal scanners and antiviruses. Our attempt at a solution was function fuzzy-based hashing, and Malfunction is our implementation.
This actually went open source this week, which we're very excited about. Comes with the starting database, the hard work of the slaving interns, which ranged from just the 2 of us to 5 at one point, as well as the link to the Git repository there if any of you would like to try it out. We've given this talk before, and we were very sad when we had to go and come to this slide and be like, it's coming soon, and then it kept being delayed over and over again.
Put it back a slide.
Oh, well.
So we ran a little bit quick. Usually this is a little bit longer, but I'm feeling a bit under the weather, and that does not mean that I'm super hungover. They won't sell it to me, I'm sorry. So this is our GitHub repository. Does anyone have any questions?
Did the dash A mean attribution? When you hit the, go back a whole bunch of slides and it was, when it said Scary Panda?
That's author.
That's the list of authors. You can input authors. If you're learning it into the database, then you need to give it the authors and any potential comments. And
Yeah,
okay.
so
that's like the analyst who wrote the, or whatever you want.
The person that wrote the
known
code.
author of the.
Yes.
Again, so it's kind of referring to the attribution in a way. So
Yeah.
if you know it.
Yeah, if you know it. You don't have to supply any of these other than blacklist or whitelist when running the commands. Because, of course, like, sometimes you just don't know. It's very hard to find out in a lot of cases. But either way, you can still detect similarity despite not knowing the author. It's just an extra tidbit that you could gather.
All right. Any more questions?
It will make sense like if people share their databases in a bigger pool.
Yeah.
Everybody has the same things.
It would become like a virus share sort of system where everyone could share it, and from that, the tool really gets more powerful once you have a lot of malware in the database. Without like too many author names or anything like that, it doesn't become nearly as useful. But yeah, potentially with enough databases shared together and just creating one giant one, you could have a very strong malware searching tool.
Yeah, that's one of our problems at the moment is we don't have a gigantic database. One, because disassembling a lot of Windows programs and even some Linux programs is strictly illegal due to the terms of service. And we don't have a lot of malware because we don't have access to like virus share. Yes, sir.
Common libraries, like that. I would imagine that could cause false positives. Let's say hashing a library that, like libc or something.
Yeah, it can, but usually it just depends on the size of the program in that case. If it imports library and then it's just a print statement, we found that they're similar. We've written programs that just imported one thing and then just had a print statement, and the only thing that changed was the text in the print statement. And they gave us a like sort of high score, but it definitely wasn't close to 100.
So in the future, we might implement like a GUI interface, or we have a web app working, though we didn't show it here. Maybe just improve the functionality of that. It's mostly working anyway. But here's our contact information. If you have any questions or want to follow either of us on Twitter. Any more questions? All right, well, thank you.